Hi, thanks for joining me. Today I'm going to be proving a theorem all to do with prime numbers. Okay, so we have n a natural number, so a positive integer, such that 2 to the n plus 1 is prime. Then I claim that n must be a power of 2. Let's get stuck into the proof. Okay, so we have that 2 to the n plus 1 is prime, and we want to show that n is a power of 2. To prove that, we're going to use contradiction. So suppose, for contradiction, that n is not a power of 2. Well, then that means that n must have an odd prime factor, because if it had no odd prime factors, its only prime factor would be 2, making it a power of 2. So certainly n has an odd prime factor, and let's call it s. So n, say, we can write in the form r times s, where s is odd, and s is not 1. So s then is at least 3. Like so. S is odd, and s is at least 3. Okay, cool. Now what I want to do is just make a quick observation. If we have x, say, bigger than y, then for all alpha in the natural number, so all positive integers, alpha, we have that x minus y always divides x to the alpha minus y to the alpha. Okay, so to see this, we'll just notice that, well, x to the alpha minus y to the alpha is just x minus y times x to the alpha minus 1 plus x to the alpha minus 2y plus dot 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 plus x to the y to the alpha minus 2 plus y to the alpha minus 1. Okay, so if you just expand out this right hand side, you're going to get most of the middle terms cancelling, and all you're left with is x to the alpha minus x times x to the alpha minus 1, which gives you x to the alpha, and then minus y times y to the alpha minus 1, which is the minus y to the alpha. Okay, so this in particular tells us that x minus y divides x to the alpha minus y to the alpha. Now, what we want to do is substitute x equals 2 to the r, y equals minus 1, and then alpha equals s. Okay, so what does this tell us? Just plugging it right into this thing here. On the left hand side we've got x minus y, which is just 2 to the r minus 1, like so, and then that divides x to the alpha minus y to the alpha, which is 2 to the r, and then we're setting alpha equal to s, so we can put an s there, and then minus y to the alpha, so minus 1 to the s, so minus 1 to the s, like so. Okay, I'm just going to bring this up here. So 2 to the r, and then this minus 1 just makes 2 to the r plus 1, like so. And then that divides, now 2 to the r to the s, well, we can use our exponent rules to write that as 2 to the r times s, but r times s is just n. So it divides 2 to the n. And then now we have minus 1 to the s, but remember s is odd, and minus 1 to the power of anything odd is always going to be minus 1. So we have 2 to the n minus 1, which is just plus 1, like so. Okay, so we know now that 2 to the r plus 1 divides 2 to the n plus 1. However, this should be sort of ringing some alarm bells, because we have that 2 to the n plus 1 is prime. So the only way this is possible is if this guy here is either 1, or this guy here is exactly 2 to the n plus 1. Now it certainly can't be equal to 2 to the n plus 1. Well, why not? Because if this guy equaled 2 to the n plus 1, then that would mean that r equals n. But if we have r equals n up here, then that implies that s equals 1. But we know s is at least 3. So that's not possible. Or if this guy equals 1, well, then that implies that 2 to the r equals 0, which means r equals negative infinity, which certainly isn't true, because then that would mean n is negative infinity, and that definitely isn't true. So because n is a positive integer. So neither of those cases work, and thus this guy here is not 1 or 2 to the n plus 1, so it's a factor of 2 to the n plus 1, and thus 2 to the n plus 1 is not prime, but that contradicts sort of our original assumption that 2 to the n plus 1 was prime. So we've arrived at our contradiction, and thus n must be a power of 2. That's the proof done. I hope you have enjoyed this video. Thanks for watching. I'll catch you in the next one. Have a great day.